Hello and welcome to the first lesson of ITE 1812 Mathematics for IT. This lesson is on number systems, and we will start by looking at the learning outcomes of this lesson. By the end of this lesson, you should be able to recognize different types of number systems as they relate to computers, and also to identify base or radix, positional notation, most and least significant digits as they relate to decimal, binary, octal, and hexadecimal number systems, and to convert values from decimal, binary, octal, and hexadecimal number systems to each other and back to the other systems. We will start with the introduction, asking the question, what is a number system? To very simply put, it is a way of counting things. So we are very familiar of counting things. So the basic type of number systems that we use frequently is the decimal system. And I'm sure most of you should be aware of or familiar with another number system called Roman system, which has its own different kinds of symbols. And we can also list out some other types of number systems like binary, octal, and hexadecimal. So these number systems can be classified according to their base. So base 2 means binary, base 8 is octal, base 10 is decimal, which we are familiar with, and base 16 is hexadecimal. Let's start with the familiar number system for us, which is the decimal system. And it comprises of 10 symbols or digits going from 0 to 9. Let's take an example, 9,875 in decimal. So each digit in this number represents two kinds of values. It has its absolute value as well as the place value. So if you take the number or the digit 5, its absolute value is 5 and the place value is 1. So you multiply 5 by 1 and you get the value 5. And if you take number 7, the absolute value is 7, the place value is 10. And you multiply 7 by 10 to get 70. Similarly, number 8 should be multiplied by 100, which is the place value, to get 100. And number 9 should be multiplied by 1000 to get 9,000. And you add up all these values, you will get 9,875. This also can be represented in this form. This number 9,875 is equal to 9 times 10 to the power 3 plus 8 times 10 to the power 2 plus 7 times 10 to the power 1 plus 5 times 10 to the power 0. So this is for that example. We can represent that in a general form to a number in any number system in this formula. So what is n here? It's any number of any base system, and dn is a digit in the nth position, and r is the base of the number system. So for the above example, r is 10, and the d is an integer in the range from 0 to r. And then we move on to quickly introduce the binary system, which has only 2 digits, 0 and 1. So take an example once again, 1001 in binary. So 1 represents 1 lots of 1, which is 1, and 0 lots of 2 is equal to 0, and 0 lots of 4, that is 2 to the power 2, is again equal to 0, and 1 lots of 8, that is 2 to the power 3, is equal to 8. And you add up all this, you get a total of 9. reminder that this is represented in the decimal number system. So you represent that in this equation 1001 subscript 2, that is representing the binary number system, which is equal to 1 times 2 to the power 3 plus 0 times 2 to the power 2 plus 0 times 2 to the power 1 and 1 times 2 to the power 0, which is equal to 9 in the decimal format. So we do not usually use or put this subscript 10 when we write decimal systems, because by default we write in decimal, we represent numbers in decimal. So we usually do not explicitly use the subscript 10. But in the notation, in other number systems, if you use numbers to denote that, it is specifically in that number system you put this subscript 2 or whatever the base that you are using. So binary system requires increased number of digits to represent a number. So you can see in this example, so in decimal system, it's just 9, but in binary system, it requires 4 digits to represent. And the binary system is very special because it is the preferred system to use in computers. So you will probably learn about the binary system, the use of binary system in computer systems very soon. And then we move on to other types of number systems, namely octal and hexadecimal systems. So in the octal system, which we called it base 8, and it uses 8 numbers from 0 to 7. So this has large string of binary numbers, can be grouped into sets of 3 digits to represent in octal. We will see some examples later on in this lecture. And then the hexadecimal system, we call it the base 16 system. It uses 16 symbols, numbers from 0 to 9, and letters from A to F. So why do we need letters from A to F? So A, B, C, D, and F, they map to 10, 11, 12, 13, and 14. 13, 14, and 15 for the hexadecimal number system. So we will take some examples to look at how this works for octal and hexadecimal number systems. Before moving on, we will also introduce what is meant by most significant bit, MSB in shortened form, and least significant bit, LSB. So what is MSB? It is the bit carrying the most weight, or we can say the most or the higher place value, highest place value. Okay, so usually if it is the leftmost bit, that's what we call the most significant bit, or the MSB. So compared to that, LSB is the bit carrying the least weight, and it is usually the rightmost bit. So take this example. This is a binary sequence. Least significant bit is the rightmost digit, and most significant bit is the leftmost digit. So MSB and LSB can be simply introduced as those two representations. And now we move on to conversion between different number systems. So we start with a simple or straightforward conversion from decimal to binary. So we first look at integer decimal to binary conversion, and how we do that is divide the decimal number successively by 2. Why 2? Because we are converting it to binary number system until the quotient of 0 is obtained. So let's take an example. That would be the better way of understanding this. So in this example, we try to convert the number 53 in decimal format to binary. So what do? We first divide 53 by 2. We get the quotient to be 26. Remainder is 1. and we keep on doing it until the quotient is 0. Okay, and we write down the remainder for every step. And this is special. This is important. The remainder sequence, and if we write the remainder sequence from bottom to top, we get the corresponding binary number, which is 110101 in the binary system. So this is how we usually convert a decimal number to binary. And then we look at how do we convert a fractional decimal to binary. Previous step was looking at integer decimal numbers, converting them to binary. So in this case, the given number is multiplied by 2 to give an integer and a fraction. Then the new fraction is multiplied by 2 to give a new integer and a new fraction. So we keep doing this process until the fraction becomes 0, or until the number of digits have a sufficient accuracy. And the digits of the binary number are obtained by reading the integer numbers from top to bottom order. So once again, we go for an example so that we can better understand this. So this is converting fractional decimal to binary. So we take the example, convert 0.6875 in binary, in decimal to binary. So how do we do that? We keep multiplying by 2. Why number 2? Because we are converting it to binary, base 2 representation. So multiply this by 2, we get 1.3750. And the integer part, we write down the integer part is 1, and the fraction part is 0.3750, and so on. So we keep on doing this until we reach 0, the fraction to be 0, and we stop it when we require certain number of decimal representation. Right, so how do we write this number? The converted binary number is 0.1011. So we take this top to bottom and we get the decimal factor to be 0.1011. Right. So we have some special remarks here to generalize this procedure, because we were looking at converting decimal to binary, but we can use the same or the similar procedure to convert from decimal to other number systems like octal or hexadecimal. So the conversion of decimal numbers with both integer and fraction parts is done by converting the integer and fraction parts separately. So if you have a number with integer parts and fraction parts, you do those separately and then combine the two answers. So it is applicable for both, for converting from decimal to binary, decimal to octal, hexadecimal, and so on. So the next remark is the conversion of decimal integer to any base R system is similar to the procedure of decimal to binary conversion. Okay, so we already looked at some examples of converting from decimal to binary, but you can do it for any number system or any base. So how will the procedure be different? The division is done by R instead of 2. So for base 2, the division is done by 2, but for base R, you should replace the corresponding value. Next point, the conversion of a decimal fraction to a number expressed in base R, a similar procedure which is explained in decimal to binary conversion can be used. So in this case, multiplication is done by R instead of 2. So basically, we try to generalize the procedure. And we will see some examples. So here we look at integer decimal to octal conversion. Example is converting the number 426 in decimal representation to octal. So what do we do is we keep dividing the number by 8 because we are trying to convert this to octal. The base is 8. And you get the remainders here and you get the quotient to be 0. That's the stopping point. So you write the remainders from bottom to top, 652 in octal system. So 426 in decimal is converted to 652 in octal representation. And if you have a fractional part in converting to octal, so you follow similar procedures what you did for the binary conversion. So in this example, convert 0.513 decimal value to octal. What you do is keep multiplying by 8 and write down the integer and fractional parts. So in this case, in this example, you won't get fractional 0. So in this example, we stop at 5 decimal points. So the answer is to 5 significant digits, which is 0.40651 in octal. So that's converting from decimal fraction to octal. And now another number system, which is hexadecimal, and some examples of converting decimal to hexadecimal. In this case, integer decimal to hexadecimal. Example is converting 348 into a hexadecimal number. So what you do, you adopt a similar procedure. You keep dividing the number by 16. Why 16 is because you are trying to convert that to hexadecimal. And you write down the quotients and the remainder ultimately until arriving at 0 for quotient. So the final answer, the converted hexadecimal number is 15C. Why do we write C? Because to represent the number 12 in hexadecimal format, we use the letter C. So 15C in hexadecimal format. And then move on to fractional decimal to hexadecimal. We once again adopt a similar procedure. So the example is converting 0.85 to a hexadecimal number, decimal value. What you do is you keep multiplying by 16. And you differentiate the, or you separate the integer part and the fraction part, and you write that in 0.D99. So top to bottom. So why do you write D? Because the representation for number 13 in hexadecimal format is D. Right. So that's fractional decimal to hexadecimal. And now we look at another type of conversion from binary to decimal. So the example is start from this binary number and then convert it into a decimal number. All right. So the given number, so let's look at the procedure here. So we write down the given binary number, which is 110011, and we also write down the positional weights. So what are these positional weights? You need to put that in 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and 2 to the power 5. Okay, so how do you get the decimal number eventually? 1 times 2 to the power 5 plus 1 times 2 to the power 4, 0 times 2 to the power 3, 0 times 2 to the power 2, 1 times 2 to the power 1, and 1 times 2 to the power 0. And you add up all these values, which are in decimal format, and you get 51 in the decimal number system. So that's how you convert an integer binary to decimal. And what happens when you have a fractional binary? So let's look at that as well. So for example, convert 0.110101 to a decimal number. So you adopt a similar procedure. You write down the binary fractional part 110101, and you write down the positional weights. So in this case, please note that the positional weights, they are negative power. All right. So here you have to multiply 1 by 2 to the power negative 1, 2 to the power negative 2, 2 to the power negative 3, and so on. And then what you do is you add up all these numbers, and you will get the fractional value in the decimal number system. So that's how you convert a binary, fractional binary, into decimal. Move on to another type of conversion, that is from octal to decimal. First example is on integer octal to decimal. So we write down the given octal number 3462, and you also write down the positional weights similar to what we did in the last example, but in this case this is octal, right? So how do we arrive at the decimal number? We write 3 should be multiplied by 8 to the power 3, 4 multiplied by 8 to the power 2, 6 multiplied by 8 to the power 1, and 2 multiplied by 8 to the power 0. And you get all the numbers, add them up, and you will arrive at 1842. So this is how you convert an integer octal to decimal. And following up for fractional octal to decimal, taking an example, 0.752 octal into a decimal number. So how do you do that? You write down the octal number, the fractional octal number 752, and you write down the positional weights. In this case, they are negative positional weights. So you have to take them to the negative powers. 0.752, 7 multiplied by 8 to the power minus 1, or negative 1, 5 to the power 5 multiplied by 8 to the power negative 2, and negative 3. And you add up those numbers, you will get the fractional decimal value corresponding to this fractional octal value. That's how we convert a fractional octal to decimal. Now another type of conversion from hexadecimal to decimal. So once again, the first example is on integer hexadecimal to decimal, and we take the example of 42AD in hex format and try to convert that into a decimal number. So how do we do that? So we write down the given hexadecimal number. We adopt a similar procedure. We write down that first, and you write down the corresponding positional weights. Positive in this case because it's a integer value, not the fractional part. So you once again write down the corresponding numbers. 4 times 16 to the power 3 plus 2 times 16 to the power 2 plus so on. And you add up all those numbers, you will get the decimal number corresponding to this hexadecimal number 42AD in the hexadecimal form. So the fractional example for the same conversion, converting 0.12 hexadecimal into a decimal number. To write down the hexadecimal number 0.1, 2, and write down the positional weights, which is -1 and -2, and you add up all the values, you will eventually get the fractional decimal number corresponding to this fractional hexadecimal number. Another example, another type of conversion from octal to binary. So you have, in this example, you have this octal number 376 in the octal format, and you need to convert that to binary. So we adopt a procedure here. So we write down the digits in the octal number, in this case 3, 7, and 6. And how do we do this? We represent each digit in the binary equivalent, 3-bit binary equivalents. So we write down number 6 in binary form as 110. So remember, this should be a 3-bit representation when you go from octal to binary. And 7 you can write 111, and 3 you can write 011. So you write the full sequence 111, so that means 7 ones and 0. You will get the corresponding binary number. So that's how you convert an octal representation or an octal number to binary. So remember the 3-bit representation. So each digit in octal system should be converted to 3-bit representations in binary, and then you sequence, or you write them in the order 11, 111, 110. You can forget the first 0 because it doesn't add value, and then you will get the binary number for this example. And similarly, if you have a fractional octal, so take the example, you take 43.0276 in octal, convert that to binary, and basically you can get the approach this as 2 separate parts. You have the integer part and the fractional part. So integer part, you have 43, and you write the corresponding 3-bit representations for that. And also for the fractional part, you write the 3-bit representations. And you then write the full sequence, including the integer part and the fractional part. You will get the corresponding binary number for the octal example. Right. So we take another conversion, that is from binary to octal. So take the integer example first. Integer binary to octal. So take an example of converting this number 10111110 to an equivalent octal number. So how do we do that? Let's look at the procedure. So we write down the given binary number 10111110, and we, in this case, we start with the least significant bit, which is 0. So basically we start from the rightmost side, or the rightmost bit, and we group this number to 3-bit groups, basically. So you have from starting from the right, you make this into groups of 3 bits. So you have the first group is 110, second one is 001, and you're left with only 1, and you can add 2 zeros, 2 preceding zeros to that number. And then you write down the corresponding octal representation. So for example, what is meant by 110, or what is represented by 110 in the octal space, that is the digit 6. Similarly, 011 represents the number 3 and 001 represents 1. So you have corresponding octal digits or octal equivalents 1, 3, 6. So you can write down those together to get the octal number, that is 136 in the octal number system. So that's how you convert an integer binary to octal number system. And then another example on fractional, which has both fractional and integer parts, trying to convert them to octal. The procedure is similar. So you write down the binary number, which has both integer and fractional parts. You do the similar thing. For the integer part, you start from the rightmost bit. But for the fractional part, there's a slight difference. You start from the leftmost bit. Okay, you start the grouping like that. Okay, so for the integer part, you have 101. So you start from the least significant bit or the rightmost bit and group them to three bits or 3 digits. And then for the integer part, you have 15. And for the fractional part, you do the opposite. What I mean by opposite is you start from the most significant or the leftmost bit, which is in this case 0, and you group them into 3 digits, 0, 1, 1, and 1. You are left with only 1 for this case, and then you can add 2 zeros to following zeros. And then you can write the corresponding octal digits, equivalent octal digits, to be 1, 5 for the integer part and 3, 4 for the fractional part. So you can write down the whole thing, the full fractional number in octal, which has both integer and fractional parts, as 15.34 in the octal number system. So that's how you convert fractional binary to octal. We now move on with another type of conversion, hexadecimal to binary. So we previously did octal to binary, and now we are looking at hexadecimal to binary. So the procedure is similar. There's only a slight difference. So let's once again take examples. Take integer hexadecimal converting to binary. Take the example 29C in the hexadecimal format, and you write to write the hexadecimal number 29C, and then what you do is you write the equivalent binary representation in 4 bits or 4 digits. So C is 12. C represents 12. But how do you represent 12 in 4-digit binary? Is 1100. So that's how 110 comes. So C is representing in decimal, it's 12. In binary, it's 1100. And similarly for 9, it's 1001. And for 2, it's 0010. And then you take them all together to come up with the equivalent binary number. So start from here, 0010, 1001, and 1100. So the whole sequence is the binary number representing this hexadecimal number. Right. So how do we do when we have a fractional part? So the next example is about that. Convert hexadecimal number A4.E to the power in the hexadecimal format. So similarly, we write down the number. We treat this as 2 parts, the integer part and the fractional part. And you have this A4 point E. And what you do is you do a similar thing. You write down the equivalent binary number in 4 digits. So for E, you write 1110, and which is number 14 in the decimal representation. And for 4, it is 0100. And for A, it is in decimal, it's 11, but in binary, it's 1010. And you put them together to get the equivalent binary representation for the fractional hexadecimal number. Okay. Right. So that's how you convert hexadecimal number, either it's integer or fractional or both combined, to a binary number. So we look at another type of conversion. This is from binary to hexadecimal. So this is similar to going from binary to octal. So this first example is on integer binary to hexadecimal. So taking the example 1100, 11110 to equivalent hexadecimal number. So what do we do is, so we first write down the given binary number and we start grouping to 4 bits. For octal, it was 3 bits. For hexadecimal, it's 4 bits. And you start from the rightmost bit or the least significant bit. So in this case, the first group corresponds to E, second group corresponds to 9, and this group corresponds to 1. And the final outcome is 19E in the hexadecimal format. So that's how you convert an integer binary to hexadecimal. And what if you have a fractional binary and you are required to convert to hexadecimal? Well, the procedure is similar. We take an example. Here you have the integer part as well as the fractional part in this binary number, and you write down that. So similarly to previous examples, so you group the integer parts starting from the least significant bit or the rightmost bit, and you group that into 4 bits. Okay, so you get B and 3B. And there's a small difference when you look at the fractional part. You start grouping that from the leftmost bit, right? So in this case, we have only 3 digits. We have to add a 0 in front to get the number. And the corresponding hexadecimal digit in this case is number 6. And the integer part is 3B.6. So the final value, equivalent hexadecimal number, is 3B.6. So that's how we convert a binary number to hexadecimal. And another type of conversion is from octal to hexadecimal. So for example, if we have 32 or 32 in octal representation, let's look at how we go about converting that into hexadecimal. So we first write down the octal number, which is 32, and then get the equivalent or the corresponding binary representations in 3-digit format. Why 3-digit format? Because this is octal representation. So for 2, we have 010, and for 3, we have 011. And then what we want to do is we need to group this into digits of 4 or 4-bit groups, right? So we start from, once again, start from the least significant bit, and we start grouping them into 4-bit groups. So here you have 0101, or the other way around, 1010. So that corresponds to the letter A in hexadecimal format. And the other one, you have to add 2 preceding zeros to get a number of, or a group of 4. And that represents number 1. So how do you convert? The converted value in hexadecimal is 1A in the hexadecimal format. 32 or 32 in octal format corresponds to 1A in hexadecimal. So that's how you convert octal to hexadecimal. And the other way around, going from hexadecimal to octal. Let's once again take an example. This is number 47 in hexadecimal format, or 47 in hexadecimal format. We first write down the hexadecimal digit sequence, which is 47. And then we write down the binary equivalent. So binary equivalent for number 7, 0, 1, 1, 1 in 4-digit groups. And the binary equivalent for 4 is 0, 1, 0, 0. And when we have that binary sequence, now, because we want to convert this into the octal system, we start grouping this sequence to 3 digits, starting from the rightmost bit. Okay, so then you have 1, 1, 1, 0, 0, 0, and 0, 0, 1. Additional 0 should be added. Okay, then you have the representation in hexadecimal 1, 0, 7. Okay, so the final outcome 47 or 47 in hexadecimal format is 107 in octal format. Right. So these are the conversions, different types of conversions that we are interested and we are looking at in this lesson. So that with that we come to the end of this lesson. I hope you would have gained the knowledge about different kinds of number systems and converting between from one number system to the other and to the other. So we basically discussed about 4 different number systems: binary, octal, decimal, and hexadecimal. Thank you for listening to this lecture. See you with another part of this course.